The fractals, as I told before, this concept born from the hand of Mandelbrot. Mandelbrot was a French mathematician, yes, that described this natural phenomenon. And what is this phenomenon then? We're describing something that is happening in the nature, okay? So it's a phenomena in nature. And what happened with this? We're talking about a very simple form, simple structures that repeat infinite times to create the same pattern and different scales, okay? So, but it's basic and it's fragmented, okay? A structure that repeats, and we will see the same at different scales. And in nature is something very common, especially when we see the broccoli, the cauliflower, the galaxies. Yeah, we have a lot of examples coming from the nature that describe a very simple shape that repeats, and build a bigger scale of the same. Yeah, the same happened, for example, with a tree. A tree starts one branch, then divides into two, and we have the same repeating infinite times to create that tree. And everything is obtained by iteration. The iteration is the repetition of those steps. Yeah, we have a basic some steps to follow to create a fractal, and we repeat all the time the same. This is called iteration, and that we create the same structure at different scales. Very important, we need these two characteristics always in the fractal. The self-similarity, that means that at different scales we will see exactly the same, and fractal dimension, that we will describe later what is that. One example, okay, that we have here in this slide is the von Koch curve, okay, the snowflake, the snow as snowflakes. To build up this is very easy. We start with a straight line. We divide this line into 3 pieces, and then we remove the middle piece, and we add 2 lines that get contact in the middle. Okay, those are the steps to build up the structure of the snowflakes. And then what we do is repeat this in every segment of this structure. We repeat it here, we repeat it here, we repeat it here, and we repeat it here. And we get this again. That is the same, but a different scale. And we will repeat it again. Yes, and we can do this here, 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 in every segment of the curve. Okay? And we will get in the end the snowflake. We can repeat this infinite times. Yeah, we can just divide every segment now in the same. Let me just clean this, and we can have this small, okay, snowflakes. And we can repeat this all the time we wish. Yeah, as we see exactly the same at different scales. Yeah, the small one, the big one. Yeah, if we zoom in or zoom out, we will see exactly the same. That is a self similarity. Okay, this needs to happen in the fractals. If there is no self similarity, then it is not a fractal. And if we just think, and we make this question now, we raise this question: are the financial markets self-similar? Yeah, so that is the first question that we need to try to answer. I don't know, what do you think? But I think that they are self-similar. Yeah, and the reason why is we have now in this slide different instruments at different time frames. But it's very difficult to say which instrument is any of this and which time frame are we talking about. It can be any of them, especially these two are very similar. These two are very similar. Yes, everything is very sideways here. So we know that it's a financial market. Yeah, that is an instrument, or we don't know exactly which one, and which time frame. And then we can start just talking about self-similarity, because we see practically the same in the different instruments and at different scales. We will see all the time this kind of, let's say now, chaotic movements up and down, okay? And have a look, we have Forex instruments, the pound and what minute, the euro 5 minutes, and they are quite similar. Then we have the Bitcoin 15 minutes, the Standard & Poor, the crude oil, Apple, different time frames, different instruments, and in all of them, we see a similar behavior. But not also the self-similarity is visual. Okay, it's not that we see all the instruments like the same with these movements up or down. We also have a self-similarity in the statistic field. Okay, statistically, there are things that you can see here. This is part of our dashboard, and you will find the dashboard in the free forecast that I showed before. This is telling you how they behave, yeah, from the statistical point of view. And we have here marked something regarding the mean. This is analyzing all the movements for a certain period of time. Okay? When we see this, we have different time frames, different instruments, but all of them tend to the same. Yeah, and the same is they tend to balance the mean. The mean tends to 0 with the different movements. Okay? Try to compensate to each other. What happened? Why we have then movements up, movements down? Why we have progression or regression? It's because of, if we see the price in the candle, we have 4 different: open, low, max, and close. The close is the one that allows this grow or drop. Okay, but all of them tend to compensate. Okay, that's the first characteristic that all the instruments share. And also this can be seen in the spectrum. Okay, the spectrum is this one, all the movements in a graphical point of view. We graphic and we put the dots for all the movements or the dispersion, and we can see that they are quite similar and symmetric in behavior. Yeah, they have a symmetrical behavior, all of them. Okay, if we see here, we see practically the same. Goes up, goes down. Yeah, we're talking about the same. Doesn't matter the instrument, the behavior tends to be the same. Is symmetric. So this also shows this compensation that we talked before. They always tend to a balance. Yeah, and that's something very important that defines the true self-similarity in the financial markets. We have a question from Harish. Structure one market may be similar to the other market around the world. It's not. I'm not catching exactly your question. Structure one market may be similar to the other market around the world. What we see in the end, if I understand your question, is everything is self-similar. Statistically, especially from the statistics point of view, we have similar behaviors shared by all the instruments. Doesn't matter what kind of instrument we're talking about, they share this characteristic. Okay, and that makes the financial markets very special. And this is what really start giving us a chance to forecast and predict what will be the coming movements in any kind of instruments. And now it's when we just start putting a barrier to the classic thinking about random markets. Yeah, markets, financial markets are not random. They have certain behavior that can be described and also can be predicted. Okay, and this is the starting point of it. Also, we talk about fractal dimensions, just to understand this very easily. We know 3 dimensions mainly: the line, the surface, yeah, and the area. If you remember the numbers belonging to each one, we have dimension 1, we have dimension 2, and we have dimension 3. Okay, the fractals doesn't have any of these dimensions. It's not 1, it's not 2, it's not 3. They have a dimension that is in between each of these. And in the case of the financial markets, when we see the movements, we see this movement, and we'll see this concept later. So they occupy part of the surface, but they don't cover all the surface, and they are not aligned. We see in this case 3 lines, so we can see more. So that means the dimension of the different kind of instruments will be between 1 and 2. Okay, and this is what we see here. The euro dollar, for example, has a fractal dimension of 1.38 based on the studies we did, and you can find these studies in the book. The pound, 1.30. The dollar yen, 1.36. Okay, so we have then another characteristic of fractals. So we can say at this moment that financial markets are fractals. They have self-similarity, visual, of course, but also more important, statistical, and also we have fractal dimension. So they can be included in this set of fractals.